Good good morning, student. Good morning, everyone. Today we are going to discuss the class 11th physics chapter number 2, motion in a straight line. Okay, right? So before that, before we enter into the our topic, I will share the one picture. Yes, clear? Okay, right. So look at this image on the screen. Imagine you are sitting in the passenger seat of this car, crushing down a perfectly straight highway at, for example, 100 kilometers per hour. Yeah, you will look out the window, and what do you see? What do you see? What do you see? The trees right next to the road are absolutely sprinting past you in the opposite direction. Correct? Right? Yeah. So the trees right next to the road are absolutely sprinting past you in the opposite direction. So they look like a green blur racing backwards as if they are late for something. Yeah. Yes. But now look past the trees. Look at those giant mountains in the background and the cloud hanging in the sky. Yeah. Are they moving? Are they moving? No. Correct. Are they moving? No. They seem to be perfectly still, tracking along with you, calmly enjoying the ride. Is it correct? So, this brings up a fascinating puzzle. If your car is the one moving forward, why do the nearby trees look like they are flying backward while the distant mountains don't move at all? Yeah. So only trees are moving. Yeah. Mountains are there and clouds are there, but only you can see that trees are only moving. Why? Correct. So the secret lies in how our eyes perceive motion relative to our position. Okay. So eyes perceive motion relative to our position. To understand this illusion and to understand how things actually move in our universe, scientists had to invent a clever trick. They decided to swing massive, complex objects like the cars, train, and even planets into a single tiny mathematical dot. Single tiny mathematical dot. Okay. Okay. So today we are going to learn how to do exactly that. We are going to dive into the world of motion in a straight line. Okay. So look at the world through this point object lens. Okay. Point object lens. And decode the exact equations that govern everything from the speeding car to a falling apple. Okay. Right. So let's get started. Now I'm going to share the one second. Now I am going to share the 3 MCQ for the quiz icebreaker. Okay. 1 second. So here you can see that here you can see that 3 MCQ for recall the earlier concepts. Clear? Okay. Which of the following quantities can become zero even when an object has undergone a net motion? You can type the answer in the chat box. Which of the following quantities can become zero even when an object has undergone a net motion? Path length, displacement, speed, none of the above. Which one is correct? Which one is correct? Which of the following quantity can become zero even when an object has undergone a net motion? Yes. Displacement. Very good. Displacement. Yeah. So displacement can become a zero even though that object undergone a net motion. It is a circular path like that. Yeah. So when we start at one position, for example A, and we entered the path at that same point A, that means displacement is zero in that case. Yeah. Okay, good. Second one, very easy one. What is the standard SI unit used to measure acceleration? Already you knew about the acceleration, mass, motion, rest, velocity, like that. Yeah. So here the important one, SI units. What is the standard SI unit used to measure acceleration? Yeah. You can type the answer in the chat box. Yes, good. Meter per second square. Option C is the correct right answer. So meter per second means it is for velocity or speed. Okay, it is for velocity or speed. So for the acceleration part, m meter per second square, m by s square. Correct. Good. Third question. If an object covers perfectly equal changes in position over a equal intervals of time, its motion is classified as this. If the object covers perfectly equal changes in position over equal intervals of time, so that motion under the what type of motion? Uniform motion, non-uniform motion, free fall, rest. Which one is correct? Yeah, yes, correct. So when you see that keyword equal changes in position over equal interval of time, that means uniform. That means uniform motion. Clear? So I can click that option A and submit. We can see the answer. Yes, first one, which of the following quantities can become zero? Displacement. What is the standard SI unit used to measure acceleration? Meter per second square. If the object covers equal distance, equal interval of time, uniform motion. Clear? Good. Okay. So now we are going to the main topic, that is motion in a straight line. Motion in a straight line. So for that concept, I am going to share the one animation so that it will be easy for you to understand the concept clearly. Yes? Clear? Okay, good. So, this session covers a concept building through the simulation. That means animation. Okay. And in the next 30 minutes, I am going to build the entire chapter's core ideas in your mind using a live simulation. And after this, in our later sessions, today you will practice MCQs and numerical problems built on exactly what we see right now. Okay. So watch carefully. Everything that follows depends on the pictures you build in your head in this half hour. Okay. So here is our one line definition for today. That is motion. What do you mean by motion? What is the definition for motion? Already you knew that. Yeah. Motion is the change in position of an object with the time. Clear? So motion is the change in the position of an object with the time. So we can take any object. So we are also one type of object. Okay. Suppose if our position changing with respect to time, that mean that mean yes, motion. Yeah, correct. Very good. Motion. So motion is a change in the position. You have to change the position with respect to him. Then only you can say motion happened. Clear? Suppose time goes. Position is there. Same position. That means rest. Yeah. 1 hour, 2 hour, time passing. But that object is still there, still at that position. You can say that that object at rest. Clear? Okay. So every equation we touch today comes from unpacking this sentence, motion. Okay. So one quick but important note before we start the simulation. This is in this chapter we treat every moving object like already I told you, a car, a ball as a point object, as a point object. Yeah, we shrink it down to a single dot in space. Clear? So you know that car has something length meter. Man has something length. Yeah, or one tree has some length. But in our physics, we consider as a point object. We consider as a point object. This is valid whenever the size of the object is much smaller than the distance it travels. Okay. Whenever the size of the object is much smaller than the distance it travels. Keep this in mind. Because here you can see that one yellow car. Yeah. And the golden ball in letter. Okay. You are all about to see are both just point object standing in for the real thing. Clear? Okay. So this is our one-dimensional kinematics laboratory. Okay, this is one dimension. One dimension means motion in a straight line, motion in a single direction. That means one direction, one dimension. Clear? We can say we can take x-axis or y-axis or z-axis, but we have to only take one direction or one dimension. So that means one dimension kinematics. So at the top of the screen, you can see that 3 tabs. First one, constant velocity. Second one, accelerated motion or turning point. Third one, free fall. Okay. We will visit all 3 in order in the next 20 minutes. Okay. On the left, you can see the control panel with the sliders. In the center, the motion track. Here, one motion track. Clear? And below it's 2 graphs. One is position time graph, another is velocity time graph. On the right, you can see that live readouts. Live readout panel giving us live numbers for t, x, v, and a. You can see the time, position, velocity, acceleration. So this will give the real data, real numbers. Okay, live numbers. Okay. So first of all, we have to know path length is the total distance actually traveled. Yeah. In our earlier classes, we studied what is distance or what is displacement. In the distance concept, we may know that path length is the distance. Yeah. So path length is the total distance actually traveled along positive. Clear? Along positive. So because distance never be negative, always be positive. Yeah. And displacement now. So displacement is the straight line change in position with the direction. Yeah, change in position with respect to time. So with the direction. So it can be positive, negative, or even zero. Already we saw in that icebreaker quiz. Yeah, displacement 0. And importantly, you must know displacement always less than or equal to the path length. That means distance in magnitude. Displacement is always less than or equal to the path length in the magnitude. So hold that thought. It will matter the moment our car reverses direction later. Clear? Okay. So first of all, I have selected constant velocity here. You can see that. Yeah, I have selected constant velocity. Notice that acceleration slider is locked. Here you can see that acceleration locked. So for example, when you select the accelerated motion, acceleration value something minus 3.0 or something else. But when we click the constant velocity, that means acceleration is locked. That means 0. So acceleration slider is locked at 0. So in this station, speed never changes. This is called uniform motion. Speed never changes. Clear? Okay. First of all, I am setting the initial position here, x0. Clear? Here, initial position x0 to 0. Clear? Okay. I am setting the initial position x0 to 0. Our chosen origin. Okay. So remember, the origin is always our choice. Origin is always our choice. Physics does not force one on us. Okay. So you may select any origin, and origin is our choice. Okay. Now drag the initial velocity v0 to 10. Okay. We can choose the 10 meter per second. This is initial velocity. Okay. Initial position 0, constant velocity, acceleration is locked. Now initial velocity 10 meter per second. So that means I am setting the initial velocity v0 to 10 meter per second. Okay. 10 meter per second. Clear? So about 36 kilometers per hour. 36 kilometers per second, per hour. Clear. So you can say that as less than 0. So since as less than 0, this stays 10 meters per second for the entire run. Clear? This stays 10 meters per second for the entire run. So for the first run, I am hiding the velocity time graph. I am hiding the velocity time graph. So only the position time graph is visible. Clear? Position time graph is visible. So you focus only on position first. Now click run. Now click run. Yeah. Good. Okay. So watch the yellow car gliding steadily to the right. Never speeding up. Never slowing down. Correct? Yes. Okay. Good. Now again, see that what's the teal position time graph below. It is a perfectly straight. It is a perfectly straight tilde line climbing at constant angle. Clear? Climbing at a constant angle. So this straight line is the graphical signature of constant velocity. That means equal position gained in every equal slice of time. Okay? Equal position gained in every equal slice of time. Clear? Okay. Now watch the live readout data. Velocity, you can see that only 10 as less than 0. Only time changes, position changes. Clear? Okay, right. So time t climbs steadily. Yeah, increasing. And position also, x also climbs with it. Clear? 10, 20, 30, 40, like that. And it reaches the 120. So climbs steadily with that time. So exactly 10 meters for every 1 second. For every 1 second, 10 meters. For 2 seconds, 20 meters. For 3 seconds, 30 meters. Like that. Yeah. Clear? You can see that. For the time 2.03, position 20.33. So for every 1 second, exactly 10 meters position traveled by that car. Clear? So this is called velocity. This is called velocity. So velocity means the rate of change of position. Yeah, you can see that. Time changes, position changes, so motion. So velocity here, you can see that rate of change of position. So we define average velocity. Average velocity means v bar equal to del x by del t. Del x means change in position. That means x2 minus x1, and del t means time changes. That is t2 minus t1. Yeah. So del x by del t equal to x2 minus x1 by t2 minus t1. Clear? So this is velocity, average velocity formula. Okay. For this motion, average velocity over any interval, first 2 seconds, last 3 seconds, any slice, always equals exactly 10 meters per second. Yeah. So again, you can see that any other time. Here you can say that 30 meters. So for every second, 1 second, 2 seconds, 3 seconds, exactly equal intervals of time in that equal interval of time, that car travels a equal distances. Clear? So because the velocity never changes. Velocity never changes. So this brings us to instantaneous velocity. The velocity at one exact clock tick. Yeah. We get it by swinging del t down towards 0. So we have to put limitation in that del t equal to 0. So then del x by del t, it becomes as dx by dt. Clear? Dx by dt. Okay, right. So this is a derivative of position with respect to time. And now here you can take the slope of the tangent to the position time graph at a single point. Yeah, you can take the slope of the tangent to the position time graph at a single point. Since this graph is a one straight line with no bends, yeah, you can see that. So since our graph is one straight line with no bends, its slope is the same everywhere. Its slope is the same everywhere, which is exactly why instantaneous velocity equals average velocity throughout the uniform motion. Okay, instantaneous velocity equals average velocity throughout the motion. Now we can recheck the slow velocity time graph and reset. Then run again. Now you can see that another one graph. Clear? So watch both graph together. Position time graph is a still tilde line. Yeah. But look at the new amber velocity time graph. So this color means amber. New amber velocity time graph below it. Completely flat. And a horizontal line sitting steadily 10 meters. 10 meters per second. Clear? 10 meters per second. So a flat horizontal line is the second geographical fingerprint you must remember. So constant velocity gives a flat velocity time graph. Constant velocity gives a flat velocity time graph. So one more idea, that is the area between this flat line and the time axis equals displacement. Height 10 meters. You can see that height 10 meters per 10 meter per second with 10 seconds. Area 100, like that. Yeah. So for example, time 12, position 120, velocity 10. So height 10 meters per second with 10 seconds, area 100 meters, like that. Clear? Okay. So check out that readout data. Position should read close to 120 because time is 12, velocity 110, so 10, so position 110, 120. Clear? Right. So the rectangle area is not a decoration, it is literally a displacement. Okay. So acceleration 0 means straight tilde position timeline and the flat velocity timeline. Clear? Okay. Now we are going into the second tab, accelerated motion. So I have clicked the second tab, acceleration is now unchecked. Here you can see that one value because it is draggable. Acceleration finally enters a picture. So already you know that acceleration formula. For average acceleration, a bar equal to del v by del d, as same as velocity position formula, position equation. Yeah. So a bar del v by del t means V2 minus V1 by T2 minus T1. Clear? This is a equation for acceleration. For the average acceleration, we have to put the del V by del T like that. And the instantaneous acceleration by stringing del T to 0. So then we can get A is equal to dV by dt. Okay. So first of all, we have to know what is acceleration. Acceleration is the rate of change of velocity. Clear? Already you know that. Acceleration is the rate of change of velocity. Exactly the way velocity is the rate of change of position. Yeah, notice the pattern. One key distinction, that is, if acceleration itself stays constant throughout the motion, we call it a uniform acceleration. Yeah, already I told you. If the acceleration itself stays constant throughout the motion, we call it a uniform acceleration. Okay, right. So this is the only case our upcoming equation will handle. So if the acceleration keeps changing, that is non-uniform acceleration. Acceleration keep changing, that means non-uniform acceleration. And it needs calculus every time. No shortcut formulas. It needs calculus every time. So now we work only with the uniform acceleration. Okay. So let's build an experiment that produces a dramatic result. A car that moves forward and reaccelerate, stop for instant and reverse. So for that, first I have to choose initial position into minus 20 meter. Initial position negative 20 meters. The car start 20 meters behind our origin. Yeah, you can see that. Behind our origin. Okay, so you can see that. Behind our origin. Right. So the car start 20 meters behind our origin, giving it room to travel forward and still reverse on the screen later. And we can choose the initial velocity 15 meter per second and initial velocity mean moving right. Yeah, here you can see the positive value. And acceleration A. Acceleration A means here minus 3.0 meter per second. So negative 3 meters per second squared. Like a driver braking, every second velocity drops by 3 meters per second. And it is set duration 12 seconds. Clear? So we can use this formula, that is B is equal to V naught plus AT. When does velocity hit 0? Setting V to 0. 0 equal to V naught 15. Okay, because V naught means initial velocity, A acceleration minus 3 and T. We have to find the T. So T is equal to 5 seconds when you put the V into 0. Okay, so you will get the T is equal to 5 seconds. Okay, right. So now run. Watch the car. Watch the car. It moves right. See the amber velocity arrow pointing forward. Amber means here yellow light. Okay. And the coral acceleration arrow. So here orange color light. Okay. So again, you can see that it moves right. See the amber velocity arrow pointing forward and the coral acceleration arrow pointing backward. Opposite to motion. When a particle is slowing down, acceleration points opposite to velocity. You are watching that live. Yeah. Here. So orange color is opposite to the velocity. Yeah. When a particle is slowing down, acceleration points opposite to velocity. So here orange color means acceleration line. So opposite to velocity. Now look at the data. Velocity is dropping. Yes. Clear. Yes. Yes. Velocity dropping. 6, 5, 4, 3, 2, 1 and 0. For 1 second, the car is completely at rest. You can see that. Yeah. For 1 second, the car is completely at rest. This is the turning point. V is equal to 0 right now. But acceleration minus 3.0 meter per second still acting. That's why the object is about to reverse direction. So this is the single most important idea of today's class. So understand this: zero velocity at an instant does not mean zero acceleration at that instant. A particle can be momentarily at rest while still being accelerated. So underline that word. Zero velocity at an instant does not mean zero acceleration at the instant. A ball thrown straight up has exactly this experience at the top of his flight, velocity 0, but gravity never once stopped acting. Clear? Okay. So now look at the graph. Now look at the graph. So here you can see that two graph. One is position time graph, another one is velocity time graph. Look at the tail position time graph. It climbs, curves over like the crest of a hill, flattens at the peak, and then curves back down. Clear? Eventually dropping below where it started. Yeah. So this bowl or hill-shaped curve is a parabola. Parabola, the graphical fingerprint of uniformly accelerated motion. So the peak is exactly the turning point here. So peak is exactly the turning point. Now look at that. Look at that velocity time graph. Amber velocity time graph. A straight tilted line starting at the 15. Yeah, sloping steadily downward, crossing 0 exactly at 5 seconds. Yeah, exactly at for something 20 second, 12 second. Okay, so 12 second, whatever else. So, but it reaches a 0 because momentarily rest at that instant. Clear? Okay. Crossing 0 velocity at 5 seconds, continue to into negative values with the slope never changing. A straight sloped line is a fingerprint of constant acceleration. The slope itself a acceleration. The slope itself a acceleration. So from this we can get the three kinematic equation. Already I told you. Here you can see that V is equal to V naught plus AT, X is equal to X naught plus V naught T plus of AT square, and V square is equal to V square plus 2AX or 2AX minus X naught. Clear? Already in your book you can see that. So these connects X, T, V naught, V and A. So they are only valid when the acceleration is uniform. That means constant in both magnitude and direction. If the acceleration changes, these equations do not apply. Okay, note it down. If the acceleration is changes, these equations do not apply. Clear? Okay. Now we are going into that numerical problem. So I will share the screen again. One second. So here you can see that one numerical problem. Sorry, two numerical problem. One. Clear? Okay. So first problem, turning point condition. A car start with the initial velocity, that is V naught, plus 15 meter per second, and undergoes uniform acceleration A minus 3 meter per second square. Find the exact timestamp at which the vehicle momentarily comes to rest. So you can see that V naught, that is initial velocity, 15 meter per second, and already you may know that the acceleration is opposite to the velocity, that is A equal to minus 3 meter per second square. Clear? Find the exact timestamp at which the vehicle momentarily comes to rest. So first of all, identify given information. Initial velocity, acceleration, momently comes to rest means final velocity must be 0. That is v is equal to 0. Clear? Okay. So here we have a car moving forward because of velocity plus 15 meter per second in our positive direction, indicated by the blue color line. Clear? Blue color line means blue velocity vector. Okay, 15 meter per second. But notice the red color vector, the acceleration. Yeah, acceleration. Acceleration is negative. So what does a negative acceleration mean when a velocity is positive? What does a negative acceleration mean when velocity is positive? It means the car is slowing down. It means the car is slowing down. That means it is deaccelerating. Clear? It is negative acceleration, or you can say that deaccelerating. So negative acceleration mean when a velocity is positive means it is deaccelerating, negative acceleration. The question asks, well, when the vehicle momentarily comes to rest. So that word very important. What does comes to rest? Translate into physics language. That means final velocity is 0. Yeah, very good. Final velocity is v exactly equal to 0. Okay. Now, step number 1, identify the given information clearly. We have initial velocity, we have acceleration. We know that our final velocity is 0 because the car stops. We are looking for the time t. Okay. Now, step number 2, we choose a kinematic equation. This equation, already we know that equation. V is equal to V naught plus AT. Clear? Okay. Right. Let's plug in the numbers. We substitute 0 for V because that car comes to rest. So 0 for V, 15 for V naught, and minus 3 for A. Okay. So next step. Clear? 0, 15, minus 3 into T. Clear? So now it is just algebra. We move the minus 3t to the other side to get the plus 3t. Clear? Yeah. Plus 3t equal to 15. Now reveal the answer. T is equal to 5 seconds. That's all. We find our answer. T is equal to 5 seconds. It takes exactly 5 seconds for the car to stop. That's why I am saying in our simulation, in time is equal to 5 seconds, the car stops momentarily at rest. And then car moving after that 0. So crossing that 0 value. But it momentarily at rest for this velocity, for this acceleration, time equal to 5 seconds. At that time, the car momentarily stops. So we get t is equal to 5 seconds. Clear? It takes exactly 5 seconds for the car to stop. This is problem number 1. Next problem. In your book, you can see that example 2.3. The ball is thrown vertically upward, V naught plus 20 meter per second from the roof of 25 meter tall building using a G is equal to 10 meter per second square downward. Determine the peak height reached above the ground and the total time elapsed before impact. So you can draw the diagram like that. Building height, G, like that. Velocity. Clear? Okay. Clear? Okay, right. So now we are not starting on the ground. We are starting 25 meters up in the air. We throw the ball up. That is a positive velocity. Gravity, already we know that gravity is always pulling it down. That is negative acceleration. So we have 2 things to find. First one is the highest point it reaches relative to the ground. Next point, second point is how long the whole trip takes. Okay, how long the whole trip takes. Clear? Okay. So first, let's tackle the peak height first. So next step, peak heights. Initial state y naught equal to 25 meter, v naught 20 meter per second acceleration minus 10 meter per second because downward. Already I told you negative acceleration because of acceleration due to gravity pulls down. At peak height, the final velocity v is equal to 0. Clear? Just like the car problem. What is the crucial physics condition at the peak height? Velocity is 0. Yeah, at the peak height, the very important keyword is that velocity is 0. Yeah, correct. So at the very top of its path, before it starts falling back down, it stops momentarily. Yeah, already we know that. So at the peak, v is equal to 0. At the peak, v is equal to 0. Now, next step. Use the velocity displacement relation to find displacement above building del y. So we know that formula v square is equal to v naught square plus 2a del y. Okay. So we want the find to distance and know velocity and acceleration, but we don't know time yet. So we use the equation that does not need time. That's why I am taking this equation v square is equal to v naught square plus 2a del y, because we don't know time yet. We use the equation that time does not need here. Clear? Okay. So we plug in our numbers 0 for final velocity, 20 for initial velocity, and minus 10 for acceleration due to gravity. Solve this. So you will get that v square 0, v naught square 20 square. So 20 square means 400, 2 into a means minus 10 del y. So del y 20 meter. Clear? So is the peak height 20 meters? No, that just from the roof. Okay, clear? Is the peak height 20 meters means it's just from the roof, right? The ball traveled 20 meters above where it started. Clear? Now, final step. Total peak height 25 meter plus 25 meter. That's why 45 meter total peak height. Okay. So the ball traveled 20 meter above where it started. Already you know that 25 meter is the height of the tall building. Above the roof, the ball travels 20 meters. So total peak height from the ground 25 meter plus 20 meter 45 meter. Clear? So the question asks for the peak height above the ground. So we must add the height of the building 25 meter plus 20 meter. So 45 meter, that's our maximum height. Now part B. Next step. Use a position time graph for the entire journey. So now for the total time elapsed before impact, this is where it gets interesting. We need the equation relating position and time for the entire journey. So we use y is equal to y naught plus v naught t plus half at square. Clear? So we need the equation like that. So let's set our coordinates carefully. Let's make the ground y naught y is equal to 0. That means our initial position y naught, right? So let's make the ground y is equal to 0. Our initial position y naught is the roof, which is at plus 25 meter. When the ball hits the ground, its final position is y is 0. So let plug that numbers. Y is equal to 0, y naught equal to 25, v naught 20, a minus 10. Clear? So next step. 0, 25, 20t and 2 cross 10. So we can cancel that 10 minus 5t square. So we will get the t square minus 4t minus 5 is equal to 0. Clear? We simply divide the 1 by 2 into 10 minus 10. So we will get the minus 5, giving us 0 equal to 25 plus 20t minus 5t square. To make this easier to solve, we can divide the whole equation by minus 5. So this gives us a much clearer quadratic equation. T square minus 4t minus 5 is equal to 0. So we need the factors of minus 5 and add up to minus 4. Yeah, we need factors of minus 5 that add up to minus 4. So those are minus 5 and plus 1. So when we multiply the minus 5 and plus 1, we will get the minus 5. Clear? When we add the minus 5 plus 1, we will get the minus 4. So this is the factors for this quadratic equation. So we will get the like that. T minus 5 into t plus 1. Already you know that the factors finding method equal to 0. So possible solution, t is equal to 5, t is equal to minus 1. Clear? So here time cannot be negative in this context. So negative, we don't need the negative value. Okay. The journey start at t is equal to 0 second. So we reject minus 1. Our answer is t is equal to 5 seconds for the total trip. Clear? So this is a numerical problem. Okay. Okay, student. That's all for today. So you can ask any questions related to the motion in a straight line. You can see that you saw that velocity time graph, position time graph, negative acceleration, and examples two problem, turning point and NCERT example 2.3. Clear? Okay. So if you have any doubt, you can ask it. Yes. Good. Thanks for all students. Very good answers. Good. Okay, students. That's all for today. Jai Hind, Jai Bharat. Thank you. Jai Vidyasati.